So before we get into the exercises from this lesson, let's just review this kind of a big idea. What I have here is I have a line, and I have a line that I have a point that I've marked right here at the arrow, and I've drawn a line through it that's perpendicular. And I've done that using GeoGebra tools, so I know that this is a perpendicular line. What I want to demonstrate what happens is if I take this line and I rotate it about this point through 90 degrees. And by the way, as I rotate the plane, think about, I'm rotating everything on the plane. So think about there's a piece of patty paper with a dot right here, and I'm spinning the whole thing 90 degrees clockwise. And as I do that, these two items right here, right, this slope triangle that I have, this one, it's a rise of 2 and a run of -3, or you could say a rise of -2 and a run of +3. So this has a slope of -2/3. It's a negative slope. As I slide through the whole 90 degrees and I get to a point where it lines up at the 90 degrees there, what I want to point out again is what happens with the rise and the run. They've changed places. Before this line that we started with had a run of -2 and a run of 3, a slope of -2/3. This new line, the line that resulted from rotating the original line through 90 degrees about this point, now has a rise of 3 and a run of 2. So this has a slope of 3/2. This has a slope of -2/3. Those slopes are opposite in sign. One's negative, this one's positive. This one's -2/3. This is +3/2. So they're also reciprocals. Literally, the rise and the run have switched places in that ratio in order to produce this new line that's perpendicular. And that's really the big idea right here, is that lines that are perpendicular will have slopes that are opposite in sign, and they will also be reciprocals.
So Robert believes the lines graphed at right are perpendicular, but Mario is not convinced. What is the slope of each line? And then it says explaining how you know whether or not the lines are perpendicular. So let's make that a little bit larger diagram. So if I look at this, so one of the lines has a slope of, it appears to be up 1 and then over 1, 2. Right? So this line right here has a slope of up 1 over 2 of 1, or 1/2. The other line, if I look at it, it appears to be, I can probably do it from here. It's down 1, 2, 3 units, and then to the right, 2. So this line has a slope of down 3, so -3 over 2. Those lines are not perpendicular to each other. They would be perpendicular if they were opposite reciprocals. In fact, if you think about the video I was just showing you, if you were to rotate about point A 180 degrees, 90 degrees, you would get to where this triangle that we observe down here, right? This triangle would rotate and eventually become this triangle over here. And notice that what was the run, the 3, it becomes the rise once it's rotated through 90 degrees. And what was the rise, right, becomes the run once it's rotated through. And the signs are opposites of each other. So two lines are perpendicular if their slopes are opposites of each other. One's positive, one's negative, but they're also reciprocals of each other. So they're different signs. One's positive, one's negative, and they the change in y and the change in x change places. So examine the rectangular right. Write an expression for the perimeter in terms of x. Well, I know that there's 4 sides of it. One of them is 2x. In fact, 2 of them are 2x long. And the other sides are x plus 3. So if I was going to write the perimeter for these, I would have 2 2x's. So I'd have a 2x plus another 2x. And then I would have 2 of these x plus 3. So I'd have x plus 3, and then one more x plus 3. And I'm going to go ahead and simplify that. If you look at it, there's 2x's, 4x's, 5, 6x's. So when I combine all of them, there's a total of 6 times x, and then I have plus 3 and 3 is 6. So 6 times x plus 6 is the perimeter. And it says, assume the perimeter is 78 degrees. Determine the dimensions of the rectangle. Well, that's interesting. So if the dimensions were, if the perimeter rather was 78, right? What are the dimensions? Well, I could figure out what x is, and if I know x, I could figure out the dimensions. One of them is twice x, and the other one would be x plus 3. It's pretty simple to solve that for x. I'm going to take away 6 from both sides, and 78 minus 6 is a 72, and that equals 6 times x. And I need to divide both sides by the number 6. And I'm ashamed to say I consulted my calculator, but 72 divided by 6 is a very nice number. It's 12, so x is 12. Now, that's not the answer to the question. That's what x is. It says determine the dimensions of the rectangle. So the dimensions of this rectangle, one of them would be 2 times 12, or it would equal 24. And the other dimension would be 12 plus 3, which would be 15. So the dimensions of that are, it's a 15 by 24 rectangle. And then it says verify that the area of the rectangle is 360 degrees. Explain how you know this. Well, if these are the dimensions, right, it turns out that the area would be 24 times 15. And if I multiply 24 and 15, 5 and 4 is 20, carry the 2. 2 times 5 is 10, plus 2 more is 12. And then I've got a 4 and a 2. You can see I get exactly 360, although it's off the screen. So yeah, when I multiply 24 times 15, I do get 360 degrees. So if the perimeter was expressed in centimeters, right, this would be 24 centimeters, and this would be 15 centimeters. And my area would be 360 centimeters squared. Okay, this problem freaked me out just a little bit because it says write an equation for the tile pattern represented at right, and I only saw one tile pattern. I'm like, what are they talking about here? And I thought about it a little bit more deeply. Certainly, if I had a tile pattern, I could represent one of the figure numbers and the number of tiles as a point on a Cartesian coordinate plane, and I think that's what's happening here. So I can see that figure 1, right, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 tiles. So figure 1 has 11 tiles. And figure number, let's see, it's 1, 2, 3. Figure number 3 has 5, 6, 7. So if I'm looking at, this is the point right here, 3, 7. So figure 3 had 7 tiles. So if that's representing a tile pattern, and I want to figure out what the equation for that tile pattern is, probably what I'm going to do is I'm just going to figure out what the slope and the y-intercept is. So the slope of those are my two parameters that I need, right? And if I knew this one parameter m, the slope, and if I knew the other parameter b, the y-intercept, that would be enough information to assert the line. So what is my slope? Well, it's the change in y values, and if you look at it, here's a y and here's a y, and I could figure out the change in y by going, for example, 7 minus 11. Notice I'm going this direction. That gives me my change in y, and then I could calculate my change in x by going 3 minus 1. Notice I'm following that same direction, 3 minus 1. So up in my numerator, I've got 7 minus 11, 7, 8, 9, 10, 11, which looks like the number negative 4. And in my denominator, I've got 3 minus 1, which looks like the number 2. So I've got a slope that is negative 4 divided by 2, or negative 2. So I know one of my parameters. I know that my slope is negative 2. And I'm just going to pick one of the 2 points. It doesn't matter which one I pick. I'm just going to select the second point here. That second point has an x and it has a y. And I'm going to use the x and y of that point to calculate b, my y-intercept. So let's rewrite that equation. So y for that particular point was 7. And I'm going to write that's y right there. Got it. Equals m, my slope, negative 2. Got it. Times my value of x, which is 3, got it, and then plus b. So now I can solve for b here, right? 7 equals negative 6 plus b. If I add 6 to both sides, I believe I get 13 is B. So now I know my other parameter, right? I know my y-intercept. Well, now that I know both parameters for this line, its slope and its y-intercept, I can write the equation of that line, which is y equals negative 2 times x, and then plus the number 13. And that's it. And you know, you could plug in the x and y's we know. For example, when I plug in 1, I do get 11 out of it. And when I plug in 3, that would be a 13 minus 6, which is also 7. That works as well. And if I plugged in 0, I would see, oh, guess what? The y-intercept is 13. And I know the figure 0 contained 13 tiles. Okay, this was kind of an interesting problem to me, and I did it 2 different ways. And one of the ways, it's in my notes that I'm posting, so when you look at the problem, you can see the one way it's on the left-hand side. Probably you'll look at that and you'll be like, Mr. Roberts, that's way too complicated. But I just found it kind of interesting. And then I thought about it and I'm like, oh, you know what, there's an easier way to do that. And I think the easier way is, you know what, it's, well, let's read it, right? So we've got 2 kinds of bats. We've got this thing called the Kittis Hog-Nosed Bat, or sometimes known as the Bumblebee Bat. There's a picture of a bumblebee bat, tiny, tiny little things, right? It's one of the world's smallest mammals. It typically weighs about 2 times 10 to the negative 3rd gram. So if you think about that, that's in scientific notation. That would be 0.002. That's what it would be. 0.002 kilograms. And then and it has a wingspan of 1.5 times 10 to the negative 1 meters. And then a giant golden crown flying fox bat. I've got a picture of one of those. Look at that. That thing is, I mean, it literally looks like it's got the face of a fox. It's a fox with wings. It weighs much, much more. It says that its typical weight is 1.6 kilograms. And it's got a much larger wingspan of 1.7 meters. Okay, you think about a meter stick in the classroom, 1.7 meter sticks. That's a pretty long wingspan. So this weight right here is about 1.6. So the question is, what do I multiply the 0.2 by in order to get this? It's saying, estimate how many times heavier a flying fox bat is than a bumblebee bat without using a calculator. So that's the thing. Let's not pick up our calculator. Just think about this and we'll be fine. And you know, if for example, I knew, let's say that something had a weight of 2 and the other one had a weight of 16, if I wanted to know how many times heavier the other one is, right, I could take the larger weight, 16, and divide it by the 2, and I would get, oh, it's 8 times heavier. So I would know it's 8 times more. So that's pretty much what we're going to do. We're going to take the weight of the fox bat and divide it by the bumblebee bat. So let me clear this ink and get these pictures out of my way. So if I do that, let's write down the weight of the flying fox bat, 1.6 kilograms, and we're going to divide that by a very small weight. It's 2 times 10 to the negative 3rd kilograms. By the way, when I do this kilogram divided by kilogram, the kilograms cancel, and this just is a pure number, right? It's just how many times bigger is one than the other. If I want to get rid of this negative exponent, I could, for example, choose to multiply both sides by 10 to, I could multiply this by the number 1 in the form of 10 to the thirds over 10 to the thirds. What's nice is now the denominator has 10 to the 0 power, which is 1. So I'm just left with this factor of 2 in my denominator. And my numerator is 1.6 times 10 to the 3rd power. So if I think about it, that's pretty cool, right? Because 1.6 divided by 2, I know that 16 divided by 2 is 8. 1.6 divided by 2 is 0.8. So what I've got right now is I've got 0.8 and then times 10 to the 3rd power. That means I'm multiplying 0.8 times 10 3 times, right? And if I do that, so I start with 0.8, and if I multiply it by 1 10, it becomes an 8. If I multiply it by another 10, it becomes an 80. And then if I multiply it by a final 10, it becomes 800. So, and I don't like how I wrote that. Let me do that again. So it's 0.8 times a 10 is an 8, times another 10 is 80, times another 10 is 800. Is that right? 1, 1, 2, 1, 2. That's right. It goes right there. So it is 800 times heavier, right? The fox bat. Congratulations. I mean, it's huge, right? But it makes sense that it would be, larger. But it's 800 times heavier than that cute little bumblebee bat that I wouldn't be afraid of. I don't like bees. I don't like bats either, I guess. But that fox bat would creep me out. So this dextographer says perform the indicated operations, and again you can see don't use your calculator, right? The point of this is to kind of think about the fractions. One of the things I want to point out, and this is often confusing to students, right? If I say 3 1/2, I think most of us understand that that's 3 plus a 1/2. What is a little confusing is if I was to say -5 2/3, we may not realize it, but that is literally a -5 and then minus 2/3, right? So it's kind of an oddity in the notation. It doesn't feel consistent with a lot of other things we write, but these mixed numbers, it's a -5 and a -2/3 together. So that'll help with some of these. In fact, let's look at A together. So on A, I'm going to rewrite this. It's -3 2/9. I'm going to write it as a -3 and a -2/9, and then I'll write plus an 8 and plus a 7/9. Now I can combine my whole number parts, right? I can combine the 8 and the -3, and when I do, I get a 5. And I can also combine right now the fractional parts, because look at them, they're both expressed as ninths. So I've got -2/9 and then plus 7/9, which would leave me 7 minus 2 is 5/9. So that one's actually pretty straightforward, right? The answer is 5 5/9. Let's try B. I'm a little apprehensive, but let's try it. So same kind of thing. That -7 2/7 is a -7 and a -2/7. And then to that, I'm going to be subtracting a 4 and a -1/5. So certainly we could combine the 7 and the -4. And when I combine 7 and -4, that's 7, 8, 9, 10, 11. That's a -11. No problem there. But I can't combine my fractional parts directly, right? Because they're not expressed with the same name, the same denominator. But it's pretty easy to modify those. If I want these to have the same denominators, I could multiply this fraction by the number 1 in the form of 5/5, and I could multiply the other fraction in the form of a number 1 in the form of 7/7. When I do that, it will turn them both into 35ths, and I could combine those because they would be like terms. So in the first instance, -2/7 times 5/5 would produce -10 35ths. So now I've got some 35ths. And then -1/5 times 7/7 would produce -7 35ths. Now, what's nice about that is I can combine those. They're both expressed as 35ths. So my answer, I guess the next step I write is -11, and then I've got a -17 35ths. And I can now combine those back into this notation. This is -11 and 17 35ths, right? -11 and a -17 35ths together. That is a little bit more complicated, but it was nice that we could review how we get common denominators so that we can combine fractions. Let's move on to C. Let me clear the screen. For C, we've got a multiplication problem here. And multiplication, this is like literally I gotta be careful. It's a 1 5/7 times a 3 6/7. You know, I'm not gonna do the multiplication with the mixed number. I'm gonna turn them into improper fractions. So 1 5/7 is the same thing as, I think, 12/7, right? So 1 is 7/7 and 5/7. You can see, yeah, that's equal to 12/7. And then I've got times, I'm going to multiply that by 3 6/7. Well, you know, the shortcut there is 3 times 7 is 21, right? And, 21. And then, so that's 21 set. 3 is 21 sevens. And 21 sevens plus 6 sevens, 3 is 27 sevens. Ugh. I don't like the look of that. So I've got 3 times 7 is 21, and plus 6 is 27 sevens. Well, if I'm going to multiply these fractions, the denominator I got, right, 7 times 7 is the number 49, but I'm not liking the numerator. I've got to multiply 12 times 27, and I have the authority of my calculator that is 324. And you're like, Robert, are you kidding? It says don't use your calculator. You just use your calculator. Yeah, that's true. You make a good point. If I was to do it old school, let's see, 27 times 12, 27 is 14. I don't know, that's 4 and 5. I got a 7 and a 2. That's a 4. That's a 2. Yeah, it's 324. There, see, I got it. So it's 324/49, and I have no idea if I wanted to, I could turn it into a mixed number, but to be honest, I always prefer improper fractions. They're easier to work with later on, so I would leave the answer right there, 324/49. The last question on this page is D, and we've got this -8 1/7, and we need to divide that by this -5 5/9. Again, it is a negative divided by a negative, so I know my result will be positive, but I desperately need to get rid of the improper fractions. So 7 times 8 is what, 56? So I've got 56 plus 1, so this is a 57. 57 over 7, and I need to divide that by 9 times 5 is 45, and 45 plus 5 is 49, and so 49 over 9. By the way, and I did just kind of, it is this negative divided by a negative, so I know the result's going to be positive, and I didn't totally ignore them, but I do feel bad that I didn't even talk about the negative symbols, but they're gone, they're out of the picture. Now if I want to divide a fraction by another fraction, right, I typically multiply by the reciprocal. So I would make this a multiplication problem and multiply by 9 over the number 49, which just does not look pretty. I don't see anything. Nothing's canceling. It's not looking great at all. Let me grab my Oh, I can't grab my calculator. You know, I'm looking at this, and I have definitely made an error, and probably some of you have been screaming at me for a while, but 5 times 9 is 45, and I was supposed to add 5 to that, which would have made this the number 50. So, and then that would make this the number 50 also. So I've got, it still is not making this pretty, but my denominator, 7 times 50 is, I don't know, 350. 7 times 5 is 35, so that's 350. Yuck. And then 9 times 7 is what 513. You might have better check that. 57 times 9, 4. That's 63. And a 336. 5 times 9 is 45. Plus 6. 45 plus 6 would make 51. So yeah, it's 513. So this quotient is 513 over 350. And I'm going to leave it there. Tired. And it's numerically, you know, whatever. Thank you. So we've got this shape here, and the question is, what happens if we rotate this shape about the origin, right there, 0, 0, 90, 45, or 180 degrees? So if I was to jump to, I guess I'll go to 45 degrees first. Let's see. That's close. 45 is right in there. You know what? Look at that. When I'm at, let's see, there's 0, and there's 45. Looks like it didn't change at all, right? So you go through 45 degrees, and you're pretty much right back the same. Then if I jump it up to 90 degrees, that's two 45s. and it looks the same again. Now I could go, and then it says to go to 180, so if I jump all the way to 180, looks the same also, right? But there's more in between, right? So for example, there's the 45-degree angle, and then the 90-degree angle, and then I can go to this one, which I didn't write down, which is like 135, and then I can go from 135 to the 180, and then we can go from the 180 to, I think every single time I add 45, I think I'm hitting another one, right? So it's through 45 degrees and you're there, through 45 degrees and you're there. So I guess any multiple of 45 degrees is going to make it look so it's just exactly the same. And the other question there is, you know, what other shape could you rotate? And it doesn't matter how many degrees you rotate it through, it always is the same. Well, I'm thinking a circle, and I don't know if you've got something else in mind, but I think a circle, you know, obviously, no matter how many degrees you rotate it through, it's not going to look any different. But rotational symmetry is what this thing has.